Boy, that sucked, didn't it? Terrible penmanship. That E. It's the dimensional change due to temperature change. Simply stated. Change, delta. Good enough? Which, did you guys say you have or haven't had physics? So yeah, you'll talk about that in there. Coefficient of expansion or contraction. Okay, and that's in here we're going to talk about the linear coefficient. Of thermal temperature, right? Expansion. Or it could be. Do what? Do what?
That symbol for linear coefficient of thermal expansion, what's that called?
To be honest with you, I don't know if that's, is that gamma? Alpha? Okay. I'm not much on the Greek alphabet, so I'll have to take their word on it. Do what? Delta, yeah. Dimensional change due to temperature change. Delta is change, right? Delta X, delta Y.
Yeah, those I'm familiar with.
Yeah. Yeah. Yeah, the linear coefficient of thermal expansion. Okay. And that's done by testing, so you can get a lot of those values will be given to you, especially so if you're buying from well, it used to be Ryerson Steel. I don't know if they even exist anymore. It used to be right across the highway. You could go to their tables, or Central Wire, I think we have some catalogs around, and they'll tell you what the thermal, the coefficient of thermal expansion is for all those materials. They already have that checked. Then it's a matter of, can you trust what their data is? So that's, or their data might say that, and they'll have a range, won't they? As far as that goes, for different values, they'll have a range that you can expect, because nothing's going to be perfect. Okay, what else about that? The units on that, kind of interesting, will be expressed in inches per inch per degree Fahrenheit, or millimeters per millimeter per degree Celsius, centigrade, what, Celsius? Okay, depending on what unit you're dealing with. So that's kind of a crazy unit, isn't it? Okay, why did that come up? There we go. Guess because of my mouse, huh? So what are we looking at there now? The equation, note, it says if a body is free to expand or contract due to temperature variations, and this is on page 223, there will be no stress induced, okay, based on the expansion or contraction. So you can find the dimensional change. The deformation is just going to be the coefficient of thermal expansion times the length times the change in temperature. Okay, and that's on page 223, equation 11.3. So the total change in length, you multiply the linear coefficient of thermal expansion times the original length times what the change in temperature was. Not what the change in temperature is, but the change in temperature as opposed to what the temperature is right now. Okay? So you have to do some adding and subtracting there, don't you? To figure that out. Yeah, I think in physics you even have some labs on this kind of stuff. No? No lab on it? Well, but see, that's all changed since we went to semesters, so in 30 years. Okay, then what? It says the body is somewhat or somehow partially or fully restrained so as to prevent the dimensional change due to the temperature variations. Internal stresses will develop, and that's what we were talking about earlier. These are generally termed temperature stresses or thermal stresses. Thermal sounds better, doesn't it? You also have a class in thermodynamics, I think, don't you? Fun stuff. An expression for these stresses, it can be developed as follows. So this is for the free, right? Free condition, maybe? Okay, then when we've got, now, if you look at that first part, is allowed to change, but what happens if it's restrained? Then the deformation is going to be the force times the length divided by the area times the modulus of elasticity. A lot for me to say. Or you can say the stress, which is P over A, right, times the length over the modulus of elasticity, depending on what you know. But if you know P and A, then you do know the stress, right? So that's just developing the equation. So then it says if you take and equate the two, you end up with the stress times the length divided by the modulus of elasticity equals the the coefficient of thermal expansion times the modulus of elasticity times the change in temperature. Okay, so what are we doing here? We're adding this right here and this right here. We're kind of combining things there, are we? So then what you ultimately have done then, so you're equating those two, so then that turns into the stress equals the coefficient of linear expansion times the modulus of elasticity divided by, multiplied by the change in temperature. So yeah, we just got rid of the length over the modulus here, didn't we? That's what we were doing, multiplying both sides. So this is the one. If you've got, now in this case, it's going to be, how do we want to say that? I personally like the word constrain. They're using restrain. I guess if you're, maybe it's from when I was a wild and crazy teenager and 20-year-old. Restrain just kind of scares me. That means they're putting me in chains or something, you know. Restrain means you can't get away, right? Restrained condition, you have to use that equation to find out what the stress. Okay? So you would have to see how much essentially you're seeing how much it could move, potentially. Well, no, we're not. I shouldn't say that. but you're looking for the stress there. Also note, let's see. Yeah, there is this table right here. Probably will be of some value to you as well. Thermal effects equations, and it says it basically that it summarizes the two preceding thermal equation or effects equations. 11.3 tells you the dimensional change for unrestrained elements caused by temperature, and then the bottom equation tells you the stress when it's restrained, and you can't get any movement. So what kind of stresses are you building up? If it's too much stress, what's going to happen? It's going to fail, isn't it? Does that happen? Sure it does. Well, hopefully not under your watch. It doesn't happen. Okay. So again, just going to be some plugging in some numbers there, right? Now they do have some couple of example problems there. We're about out of time. Well, what we'll do then is I'll just give you the, since we're not going to get through all that, I'll give you a couple of the simple problems to do for that, but not the ones that are restrained. How's that sound? So, wrong folder. So for homework, something we can talk about Friday. Let's plan on doing problems 11.1. This is on page 240 in your book. 11.1, 11.3, 11.4, and 11.5. Then for the second section, the thermal effects, just do problem 11.6. We'll save 11.8 for later. I was planning on doing that, but we'll just, so 1, 3, 4, 5, and 6. And most of those won't be too, actually 11.1 is probably going to be the worst one. Yeah, 11.1 and 5. The other ones will be pretty straightforward. Okay, those you'll have to do a little bit of work. Otherwise,